Hello students, here we are going to learn about chapter 1 in our 12th volume 1 book, which is application of matrices and determinants. Okay, in this chapter we are going to study about the four methods. One is matrix inversion method, second one is Cramer's rule, and third one is Gauss elimination method, fourth one is rank method. To know all these methods, we must know how to find these things. That is, how to find the inverse of a non-singular matrix, rank of a matrix, elementary row and column transformation, consistency of system of linear equations. So first we will see the basics of the things, and then we will move to these four methods one by one. Now we are going to see inverse of a non-singular matrix. To know the inverse of non-singular matrix, first we know that what is adjoint of the matrix. The definition of the adjoint of the matrix. Let A be a square matrix of order n. Okay. Then the matrix of cofactors of A is defined as the matrix obtained by replacing each element Aij of A with the corresponding cofactor Aij. That is, we have to find the cofactors of every element in the A matrix. Okay. After finding the cofactors, we find the adjoint of the matrix. That is, the adjoint matrix of A is defined as the transpose of the matrix of cofactors of A. It is denoted by adjoint of A. That is, after finding the cofactors of the particular matrix, we just take a transpose. Then the matrix is said to be adjoint of the respective matrix. Okay. Now we will see definition of inverse of a square matrix. Let A be a square matrix of order n if there exists a square matrix B of order n such that AB equals to BA equals to IN. Then the matrix B is called an inverse of A. That is, two matrices A and B are said to be inverse of each other. Means the product of the matrix should be identity, where I is identity matrix, either in the same order or reverse order. Both should be identity. If the result is identity, then the matrix should be inverse of each other. We are going to see how to find the inverse of a 3x3 matrix. Okay, that is problem. Find the inverse of the matrix 2, minus 1, 3, minus 5, 3, 1, minus 3, 2, 3. That is, we have to find the inverse of this particular matrix. First, assume that let A be the given matrix. So write A equals to this given matrix. Okay. Now we are going to find the determinant of the matrix. That is, determinant of A equals to, write the matrix with the symbol determinant like this. Okay. This is the first row, second row, third row, first column, second column, third column. Now we are going to write the determinants. First, find the cofactors of the first row. First, cofactors of 2. Cofactors of 2 is, we have to leave the corresponding column and row remaining these four elements. Okay, 3, 1, 2, 3. So we have to cross multiply. 3 3s are 9, 2 1s are 2. So 2 into 3 3s are 9 minus 2 1s are 2. So we have to put the opposite sign. Here plus 2 is coming, so we have to put minus 2. Like that, second element we have to put minus. Okay, and then already one more minus is in that number, so put other minus 1 into the cofactors of 1 is leave this element and this row element. So cofactor minus 1 is minus 5, minus 3, 1, 3. So minus 1 into 5 3s are 15, minus 15, 3 1s are 3, minus 3. So we should put plus 3, and then plus 3 into cofactors. This is, we have to eliminate this, and cofactor 3 is minus 5, minus 3, 3, 2. Okay. So 3 into 5 2s are 10, minus 10, and 3 3s are 9, minus 9. So we have to put plus 9. Okay. Then 2 into 7, 9 minus 2, 7. So minus into minus plus. So plus 1 into minus 15, plus 3, minus 12. Okay. Then plus 3 into minus 10, plus 9, minus 1. Okay. Then 2 7s are 14, 1 12s are 12, minus 12 means 14, minus 12, minus 6. So the determinant is minus 1, which is not equals to 0. If the determinant is 0 means A inverse does not exist. So the determinants must be not equal to 0. Okay. So for a non-singular matrix, definitely the determinant must be not equal to 0. So for singular matrix, the determinant is 0. This is a non-singular matrix. So therefore determinant is not equal to 0. Therefore A inverse exists. So now we have to find the cofactors of each and every element. Then only we are able to find the adjoint. Okay. So to find the adjoint of A, we just write the cofactors of each and every element. First write the cofactors of 2. Cofactors of 2 is, we have to leave this corresponding column and row 3, 1, 2, 3. I write here. And cofactors of minus 1 is, we have to leave this and this, remaining minus 5, minus 3, 1, 3 here. And cofactors of 3 is, we have to leave this and this, minus 5, 3, minus 3, 2 here I write. And cofactors of minus 5 is, we have to leave this, minus 1, 3, 2, 3 I will write here. And cofactors of 3 is, we have to leave this and this, 2, minus 3, 3, 3 I will write here. And cofactors of 1 is 2, minus 1, minus 3, 2 I will write here. Cofactors of minus 3 is, we have to leave this, minus 1, 3, 3, 1 like this. Cofactors of 2 is 2, 3, minus 5, 1 here. Cofactors of 3 is, we have to leave this, 2, minus 1, minus 5, 3 I will write here. So here we have to write all the cofactors of elements. So we have to put the sign like plus, minus, plus, minus, plus, minus, plus, minus, plus. So this is the method of finding the cofactors. We have to take the transpose. So for adjoint of A, we have to take cofactors of each element and then find the transpose. Okay. And by eliminating this, we have 3 3s are 9, 2 1s are 2 plus 2. So we have to put minus 2, 9 minus 2. Minus symbol is there. I put minus, and 5 3s are minus 15, 3 1s are minus 3. I will put plus 3. And then 5 2s are 10, minus 10, 3 3s are 9, minus 9, plus 9 I will put. And minus sign is there. 3 1s are minus 3, 3 1s are minus 3, and 3 2s are 6, minus 6. And 2 3s are 6, 3 3s are 9, minus 9 I put plus 9. So minus into 2 2s are 4, 3 1s are 3, plus 3 is minus 2 minus plus 3 is there. I will put minus 3 here. Minus 1 3 3 1, that is minus 1 into 1, minus 1, 3 3s are 9, minus 9. Again put minus here, minus sign. 2 1s are 2, 2, 5 3s are 15, minus 15 is there. So I put plus 15. So 2 3s are 6, 5 1s are 5, plus 5, minus 5. Transpose. So then 9 minus 2, 7, minus 15 plus 3, minus 12. Already minus is there. So minus plus 12, minus 10 plus 9, which is minus 1, minus 3, minus 6, minus 9, plus 9 will come. 6 plus 9, 15. 4 minus 3, 1. So minus is there, minus 1. So minus 1, minus 9, minus 10. 2 plus 5, 15. 17, minus 17. 6 minus 5, 1. So we have to listen carefully to the bracket and where we have to put this sign. Okay. If the position is changed, means everything will be collapsed. So listen carefully, the sign before the bracket, after bracket. Now we are going to see some important properties of inverse of a matrix. Okay. That is, if A is a non-singular matrix. Non-singular means the determinants should be not equal to 0. Okay. Then determinant of A inverse equals to 1 by determinant of A. So both are equal. Then A transpose the whole inverse equals to A inverse the whole transpose. Both are equal. So lambda A whole inverse equals to 1 by lambda into A inverse, where lambda is a non-zero scalar. So both are equal. So this is the result which will be helpful to solve problems. Okay. Second one is, let A, B and C be square matrices of order n if A is non-singular. That is, non-singular means determinant not equal to 0, and AB equals to AC, then B equals to C. Okay. This is called left cancellation law. Here A, B equal to AC. A is present left, so we have to cancel A and A. Result is B equals to. This is called left cancellation law. Similarly, let A, B and C be square matrices of order n if A is non-singular and BA equals to CA, then B equals to C. Here A is present right. This cancel right, so this is called right cancellation law. So these are the result which will be helpful to solve the problems. Fourth property is, if A and B are non-singular matrices of the same order. then the product AB is also non-singular, and AB inverse equals to B inverse A inverse. That is, A, B are non-singular matrix of the same order means either 3 by 3 matrix or both are 2 by 2 matrix. Okay, if both are same order means then the product is also non-singular. Then we can write this equal to this. That is, AB the whole inverse equals to B inverse into A inverse. Fifth is, if A is non-singular, then A inverse is also non-singular, and A inverse the whole inverse equals to A. Both are equal. Sixth is, if A and B are two non-singular matrices of order n, then adjoint of AB equals to adjoint of B into adjoint of A. So these are the properties which are going to useful to solve the problem.